Benford's law, a statistical anomaly that proves in the universe of data, numbers are never distributed fairly. If we collect organic data, from national populations and stock market fluctuations to the lengths of rivers, we find a single, consistent structure. Intuitively, we assume the probability of every digit is uniform. But in reality, numbers don't grow linearly, they grow logarithmically. Digit 1 consistently dominates 30.1% of the data. This pattern declines precisely down to digit 9, which leaves a probability of less than 5%. Violating this pattern isn't just a coincidence, it's a strong indication of manipulation. Let's dissect why. The year was 1938. Physicist Frank Benford noticed something peculiar in a book of logarithm tables. The early pages, containing numbers starting with 1, were dirty, torn, and stained from constant use. But the pages for digit 9 were pristine. This physical evidence proved that humans naturally encounter smaller numbers far more often than larger ones. Remember that weird logarithmic line from before? It turns out, this pattern has a source code. It's called the 1/x curve. Look at digit 1. In the real world, small numbers are, quote, kings. If we calculate the area under this curve, it is exactly the same as the physical width of digit 1 above. Mathematically, this area is the natural logarithm. Now compare it to digit 9. It's way out on the edge, the curve flattens out. The area? Narrow. The probability? Just leftovers. So Benford's formula is really just comparing areas. We switch to log 10 just to make it human readable. But the core is simple. Probability is just about how much space you take up under the curve. Warning: Benford's law is not magic. It does not work on random lotteries. In a lottery, every number has an equal chance. The graph is flat. No bias. It also fails on constrained data, like human heights. Adults are usually between 160 and 190 centimeters. Almost all start with digit 1. That's not Benford. That's just constraints. For Benford to work, the data must be free to grow. It needs to span multiple orders of magnitude, from tens to hundreds to millions. Only then does the pattern emerge. So what is this law actually used for? The answer: catching fraudsters. Suppose we have thousands of tax records. We strip away all the other numbers and focus entirely on the first digits. If we map this into 3D, authentic and natural financial records will always obey Benford's curve. The pattern fits perfectly, nothing out of the ordinary. But when humans try to fake numbers, we are terrible at generating random data. People tend to overuse middle numbers, like 5 and 6, to make it look natural. The result? The curve is broken. The pattern is shattered. Fraud detected.